Hello, ladies and gentlemen. Welcome to one of the best chapters all semester long, and that is the chapter on black holes. Black holes, because they show up in so many movies and things like that, a lot of people know something about black holes, but we're going to get into the scientific details. First off, where does a black hole come from? Well, basically, it is the death of very, very heavy stars. Our sun will never go into or turn into a black hole. You must start with a star that is 10 to 100 times more than the mass of our star. So our sun is just not massive or large enough to become a black hole. Now, after that star goes supernova, and as you recall, there is an explosion outward, and Newton's third law says for every action there's an equal and opposite reaction. There is an implosion inward. And the force of that inward explosion is so great that it will make a neutron star. Protons plus electrons get squished together to make neutral neutrons, and neutrons can be packed very tightly. If the remaining neutron core is 2 to 3 times the mass of our sun, what will result is a black hole. So you have to have a huge star so that after it goes through this massive explosion, you still have 2 or 3 of our sun's mass left in order to make that black hole. So a black hole is a collapsed star. It has around it incredibly intense gravity. And it causes near it a curvature of space and time to such an extreme extent that light itself cannot escape, making it black. And we'll explain more about that in a little bit. Something that is fun for me is when I was very young learning astronomy, black holes were theorized on paper. They were theorized on mathematically. But it is not until the last 20 years or so that we have a lot of observational evidence to indicate that they really exist. So within my lifetime, I have seen black holes from being some wacky idea people came up with to having a lot of observational proof for, and that's pretty nifty. So let's answer one question at a time. First off, why are black holes black? We always talk about the fact that gravity itself cannot escape. Well, why can't? Did I say gravity? Light itself cannot escape. So why can't light escape from one of these objects? In order to explain that, we have to go back a ways, and we're going to have to talk a little bit about our old friend, Sir Isaac Newton, and we have to talk about what it actually means to orbit something. Here's how it works. If you're playing catch or you're playing baseball and you throw a ball perfectly horizontally, it has 2 kinds of motion. It is going to have a horizontal speed that will be dependent upon the arm of the thrower. It also will be pulled down to the earth by gravity. Gravity is going to try and pull it downward towards the earth. Well, if you have a wimpy arm, and I have a wimpy arm, I am not a good thrower, the ball is going to go before it actually hits the ground. If you have a good, like Major League Baseball arm, 100-mile-an-hour arm, or at least somebody who plays softball more than I do, you can throw it a lot faster horizontally, and that fast horizontal velocity will mean that it will go a lot further before it hits the ground. So how far it goes horizontally is directly dependent upon how fast it was pitched, if we're assuming it's pitched from the same height off the ground. So what does that have to do with black holes in orbit? Well, we have to explain what it means to be in orbit, one object around another. Sir Isaac Newton, who lived back in the 1600s, had a crazy idea that nobody before him ever had. And he said this: if you go to a mountain high enough and you have a little cannon and you shoot it with a little bit of powder, it's going to go and kind of not go far before it hits the ground, just like the pitched baseball. You shoot it with more powder, and it's going to go a little further before it hits the ground. And more powder, and more powder, and more powder. But then Newton had an idea that was totally wacky. He said, because the force of gravity always pushes or pulls towards the center of the Earth, no matter where you are on this path or on this trajectory, he said, if you launch this object with enough velocity, enough horizontal velocity, instead of going a long way and falling, it's going to go all the way around the Earth before it hits the ground. And if you shoot it with a fast enough speed, it's going to fall all the way around the Earth without hitting at all. And that is actually what it means to be in orbit. Orbit means falling without hitting. This picture that I've been drawing all over here, this picture is actually from one of the books published by good old Sir Isaac Newton back in the early 1700s, when he was trying to explain this concept of orbit. Almost 300 years before we actually launched someone into space, he came up with a key idea. So the concept of orbit is falling without hitting. And it basically means you have to shoot something with a large sideways or horizontal velocity in order for it to fall all the way around without coming down again. As you can imagine, how fast you must shoot this thing is going to vary with altitude. And here's something that's kind of wacky. If you want an object to be shot at a speed so that it will not fall down again in a low Earth orbit, you have to go pretty fast, somewhere in the neighborhood of 17,000 miles an hour. Those are the type of speeds that are on the International Space Station, the Hubble Space Telescope, and other things that are orbiting the Earth. As you go higher and higher and higher, here's what's kind of crazy. The velocity actually gets slower. High Earth orbit, it'll go down to 10,000 miles an hour, 5,000 miles an hour, 6,000 miles an hour, and by the time you get so far away from the Earth that you're by the moon, in order to orbit, the moon only has to have a sideways velocity of about 24,000 miles per hour. Those of you who have had some physics, what's going on here is there is a trade-off between kinetic energy, which is speed and energy of motion, and potential energy, which is height or altitude. So in a low orbit, an object has lots and lots of kinetic energy and a small amount of potential energy. As it goes to a higher altitude, kinetic energy is reduced and it has a small amount of kinetic energy, and it's trading height for speed. And at the high orbital altitudes, it's going to have a lot of height, but very little speed. So not everything in orbit is going to be going the same speed. It'll depend upon how high it is above the surface of the Earth. One of the other interesting phenomenon is the concept of weightlessness. Now here is a picture of one of the astronauts in the International Space Station. The International Space Station is about 250 miles high above the surface of the Earth, and astronauts in the ISS can float around. And I'm sure somewhere in your life you've seen lots of pictures of astronauts floating around space stations or space capsules, and it's commonly referred to as being in a weightless environment. Well, here's one of the things that's a little wacky. Weight is defined as force of gravity. So weight is force of gravity. And if you think about it, here's how this works. The moon is about 250,000 miles away from the Earth to the moon. This picture here is not to scale. So the distance Earth to moon is about 250,000 miles. There is enough force of gravity. The force of gravity is big enough for the Earth to hold the moon at 250,000 miles away. But yet astronauts that are only 250 miles away, the force of gravity on them is so small that they can float. It doesn't make any sense. So what the heck is this concept of weightlessness because if the Earth has enough gravity to hold something that far away, it certainly has enough gravity to hold the International Space Station 250 miles above the Earth. So what exactly is weightlessness? Weightlessness is this concept of falling without hitting. If you've got an object that is, even if it's the International Space Station or the Space Shuttle, if it's moving with a big enough horizontal velocity, it is going to fall, but it's not going to hit. And that includes everything inside of the International Space Station or the Space Shuttle, and that means that includes astronauts. So the people who are in these spacecraft are actually in a state of free fall. They are continuously falling towards the Earth, but they are just not ever hitting. I use the analogy, it's kind of like if we took you up into a camper, a big camper, and 250 miles above the sky and dropped you, no horizontal velocity, and just dropped you. All the time that you were falling, you would feel weightless. You would be floating around like these folks are floating right here. But of course, here, you would hit really hard because you do not have the sideways velocity to protect you. This collection of pictures are around an aircraft that is used by the military and used by NASA to actually simulate weightlessness. It has the nickname, the Vomit Comet, and that is its nickname, not its official name. But what they do to give astronauts a little bit of zero-G experience is they take them up to very, very high altitudes. The pilot flies in a tight turn really high up, and for about under 2 minutes, the astronauts can experience zero Gs. You get a tiny flavor of this if here's a railroad track, and here's your car, and you drive over that railroad track really, really, really fast, and there's a hump, and you catch a little air, and your little hiney comes up off your seat. If your hiney comes off your seat when you go over the railroad track, you are experiencing a tiny fraction of weightlessness. Well, to get these astronauts, to give the astronauts the same experience, what they do is they make them fly over a really big bump, and they have a couple minutes of weightlessness. I'm going to ask you to watch a couple videos. The first one here is cats in zero Gs. This was back in probably the late 40s, 1950s. And this same kind of situation, they take cats up into the aircraft, and that's kind of fun to see the cats in that environment. And then the next video is going to talk more about this concept of weightlessness because it's kind of wacky. All right, that'll end this lesson. We'll see you next time.